I think we did this last theorem. So should we just recall this theorem again, the proof?
We can review that part because it was a bit.
Yes, you want to review this part again?
Yeah.
Okay. So let us see the statement. So it is called the polynomial root mod P theorem. So the statement says, so P is a prime number, and you have, so P is a prime number, and let fx be the polynomial like this: a0 x power d, a1 x power d minus 1 up to ad of degree d, that is greater than equals to 1 with integer coefficients. And the condition is that P does not divide a0. Then this this congruence fx congruent to 0 mod P that has at most d incongruent solutions. I think
Okay.
statement is fine, right?
Mm-hmm.
Right. So here we'll prove by contradiction. So that is there exists at least one polynomial, suppose capital X with integer coefficients, and all the remaining things are same, such that it has more than more distinct roots modulo P than its degree. So that is the contradictory assumption we are doing, right?
Sorry, let's see. At least one
Yes.
polynomial fx with integer coefficients. P does not divide a0.
Yes.
More distinct roots. Okay, more roots than
Yes,
its
then its
degree.
degree. Right. So this
Okay.
is the yes. So we have to prove that it has at most d incongruent solutions. So only a contradictory assumption that I'm assuming that it has more distinct roots than its degree, right? So other conditions are all same. So let us take fx like this: capital A0 x power d, a1 x power d minus 1 and up to ad, where we are choosing this polynomial fx such that it is d is the smallest such degree. So first polynomial where it occurs, I am choosing that. So now, since it has more than d distinct roots, so let the roots be r1, r2 up to rd plus 1. So this be the distinct roots modulo P. And to the solutions to this congruence in mod P. Right. So now, if I substitute, if I evaluate the function or this value of fx at r and subtract from fx, then we have this condition, right? A0 x power d minus r power d, a1 x power d minus 1 minus r power d minus 1, and so on up to a d minus 1 x minus r, because the last term will get cancelled out because last term is constant. A d will get cancelled out.
Yeah.
So now we can see that from every term like this, that is of the form x power I minus r power I can factor out this linear factor x minus r, right? So this whole thing fx minus fr, so this I can write it as some x minus r times gx.
Okay.
Right. So now what is the degree of gx? Gx is 1 degree less than that of fx because I have taken out x minus r, right? So gx is some b0 d minus 1 x power b1 x power d minus 2 up to bd minus 1.
Okay.
So what I can write is, so I can send this fr to the other side. So fx I can write it as fr plus this quantity. Okay, so now I have these are the set of distinct roots in modulo P. So if I substitute r equals to r1, then I have fx equals to f of r1 plus this quantity. Just I am substituting r equals to r1. Right, now I know that r1 is a root of fx. So f of r1 or rather than r1 is a solution to this congruence, right? Fx equals to 0 mod p. So f of r1 will be 0 mod p.
Okay.
Right? So in this, if I take this equation modulo p, then this one is gone because it is 0 mod p. So I am only left with this part.
So from fx from FR1,
Right.
you're saying since it's a solution, it is congruent with the zero mod P.
Yes, yes. R1 is a solution to this congruence, right? Fx equals to 0 mod p. So if I substitute R1, it will become 0.
So Fx is equal to x minus R1 G dx and modulo P.
Right.
So you're saying FR1 modulo P is Fx?
No. F of R1 is 0 mod p. This much. This is we can say because R1 is a solution.
So you're saying FR1 is 0. That's why you include it in
Yes,
the
yes.
last
If
line.
since if R1 is 0 mod p, so if I take modulo to this whole equation, so then this part is gone, right? This is 0.
Okay.
So I am
With
left with
Fx.
only this thing, this and this.
Okay.
Right. So now I know that fx has d plus 1 distinct incongruent solutions. These are these quantities. And since they are incongruent, R1 is not congruent to any Rk, where k is greater than equals to 2, right?
Wait a second. So you're saying Fx is also congruent to 0, not P.
Yes. So this I have assumed already, right? So this has d plus 1 incongruent solutions, distinct incongruent solutions, right? So these are the solutions, like R1, R2 up to Rd plus 1. And since they are
Okay.
distinct and incongruent, so R1 is not congruent to any of the Rk's for k greater than equals to 2, right?
Okay.
Right. So then what I can have, what I have that gx. So since I have taken out this factor of x minus R1, so the remaining things from R2 to Rd plus 1, these are the roots of gx, right? So gx has roots R2, R3 up to Rd plus 1. But gx, what is the degree of gx? So degree of gx is d minus 1, right? D minus 1 is the highest power.
Yeah.
So what I have shown, so from R2 to Rd plus 1, there are d roots, right? So what I have shown that gx has d distinct incongruent solutions modulo p. So that is a contradiction because we chosen fx to be the smallest one. So to have the smallest degree such that it has more than the number of solutions than the degree.
Okay, so you're saying g of x has roots R2 to Rd plus 1. Okay.
Right.
And what about R1 is not the root of
No,
gx?
R1, because R1 we have taken out, right? Because R1 we have taken
Oh, we
out as a
already
factor.
removed it. Okay.
Yes.
And then you're saying gx has the distinct incongruent roots mod p.
Right.
So how do you get to that very last one, last conclusion?
Yes. The conclusion is, but gx is degree is d minus 1, right?
Yeah.
So degree of gx, you can here see it is d minus 1. But we got d distinct solution. So it is more than the degree, right? But that is the contradiction because we assumed fx to be the smallest one. Fx to be the smallest one such that it occurs. It will have the smallest degree where it has more than distinct roots than the number of than its degree. But we can provide a smaller polynomial that also satisfies that condition. So it is not possible.
Just scroll down a little bit.
Yes.
Okay, so in the previous line, you're saying EDX has roots from 2 to D plus 1.
Right.
GX has D distinct roots from D plus 1 to 2, no?
Yes. Two R2, R3 up to Rd plus 1. These are Rd distinct incongruent roots modulo p. But the degree of gx is d minus 1. So that is that it has more distinct roots than its degree.
That's why it's a contradiction.
Yes.
Okay.
Right?
Yeah.
Okay. So I think this is fine. So now we'll move on to the exercises of this chapter 8 we are doing. So
Mhm.
okay, so the first one they're saying is, so suppose A1 is congruent to B1 modulo M and A2 is congruent to B2 modulo M. Then first part is, so verify that A1 plus A2 is congruent to B1 plus B2 modulo M. Yes, tell me how to, this is not very difficult. Tell me.
So it's saying to verify.
Right, A1 plus A2 is congruent to B1 plus B2 modulo M.
There was a property. A property, I remember.
Property, yes, not exactly property, just from definition we can do. So the thing is, A1 is congruent to B1 modulo M. So what does it say? By definition of congruence, what is the definition?
It was something like n is like a divisor of a1 minus b1.
Yes, yes. So from the first condition, what you have is that M divides A1 minus B1, and from the second condition, I have A divides A2 minus B2. Yes. So then, how will you use that?
N1 minus b1 is equal to nk.
Right.
Then
So A1 minus B1 equals to mk, and A2 minus B2 equals to some
n m n
L, suppose.
n. Okay.
Right. So yes, then
Then maybe we can just ask both of them.
yes, we can do that. So what if we add? So adding both. So we have A1 plus A2 minus B1 plus B2. So this is M of K plus M. Yes. So I think this follows. So it happens that M divides A1 plus A2 minus B1 plus B2. Yes.
Right.
So hence A1 plus A2 is congruent to B1 plus B2 modulo. Okay.
Mhm.
So
Right.
this is fine, right?
Yeah.
Okay. So the second part is A1 A2, the product is congruent to B1 B2 modulo.
Maybe can we do the same?
Same means what do you want to do?
Yeah, so instead of adding, we can multiply both. I mean, we can pass first, maybe A1 will be equal to nk plus B1, and then A2 will be equal to,
B1 and A2 is okay. Then multiply, you're saying.
yeah. Now we can multiply.
So multiplying, I have A1 A2. It is Okay, so if I expand, what will happen?
You will have n squared KL
Right.
plus nk v2 v1 nl plus
Yes.
v1 v2.
Right. So if I
And then
send
you
yes
can pass
b1 b2 to the other side,
uh,
and we can take m common from the remaining factors.
n common, right?
Right. So this part is, so it says that m divides a1 a2 minus b1 b2.
Mm-hmm.
Okay.
Right.
Right. So I think this is fine. So the second problem is, so suppose, so it is given that AC is congruent to BC modulo m, and also assume that GCD of C comma m, that is 1. Then prove that A is congruent to B mod m.
Mm. Okay, so the GCD of C and N, I mean, we can say like CX and Y equal to 1.
Okay. CX plus ASS. So GCD is 1. So this implies CX plus MY equals to 1.
Okay,
So
plus
for some
1.
integers x and y, yes.
And then we also have that maybe we can say we can do it like AC minus BC equal to NK, and then we factor C.
Okay. Okay, let's write down. So okay. So next.
We factor C.
Okay. How will you replace that if you factor C?
CAB. Okay. I mean, from there we can say that N is a divisor of I minus B.
No. How will you say that?
Like we cannot say that. I mean, because N is on the
No.
right.
So here actually you have to use this condition that GCD is 1. So since this equation holds, so CX is congruent to 1 mod M, right? If I take modulo,
You take module of you take module N for to each
yes,
member.
modulo M, if I take the equation, then it becomes CX is congruent to 1 mod M, right?
So when you apply module N, you apply for each member, right?
Yes, each member.
So CX module N, what is the answer? CX module
If I
N,
apply modulo M, then this becomes 0, right? Because it is divisible by M.
right?
So only CX is left and 1 is left. So CX is congruent to 1 mod M.
Okay.
Right. So here,
Mhm.
what you can do is, So this equation also, if I apply modulo m, so this is congruent to 0 mod m, right?
Why is congruent to 0?
Yes, because this is divisible by m, right? This will
Right.
become 0, right?
So yes, you're saying I minus b c minus 0 is a divisor of
Yes,
is a
that is,
divisor of that.
yes, yes. So now, if I multiply by x on both sides, so that I can do. So I multiply by x, so this will still become 0 modulo m, right?
Okay, okay.
But I know that this cx is 1 mod m, right? So
Okay.
this will go in the next equation. So a minus b is congruent to 0 mod m because
So
cx is 1.
you're saying you apply module n to everything again,
Yes, yes.
and the left cx would become 1.
Right.
0
So
is
now
still 0.
b I can send to the other side. So a is congruent to b mod m.
So when you apply module, you don't leave the module on the left because
Yes, yes.
even though you have
Just it is just convention. We write modulo this side only.
only on the right.
Yes, yes.
Okay.
So this is fine, right?
Mm-hmm.
Okay. So next one is, so 3. So it is saying that find all incongruent solutions to each of the following congruent. So the first one is 7x is congruent to 3 modulo 15. So they're asking to find solution to this equation.
Okay, I remember something.
Yes.
So the GCD of A and M.
Yes. So here 7 and 15 GCD is 1, right? So
Yep.
solution exists. So that is true. But how to find the solution?
I remember we find one solution first, and then we have like a formula to find the other solutions.
Okay. Let us. So yes, how to find the first solution?
We can do the Euclidean for now.
Yes, yes. So Euclidean we can do. So the thing is, so GCD of 15 and 7. So this is 1. So now we can apply the Euclidean algorithm. So tell me. So 15 is,
2 times 7 plus 1.
oh, this much is only. So I have 1 equals to 15 minus 2 times
2,
7, right?
2 times 7.
So what I have is, so basically what it is showing is, so if I take modulo 15 to the whole equation, then what I have minus 2 times 7, it is congruent to 1 mod 15, right?
If you take module 15 to everything you're saying,
Yes.
to which equation? To A?
Yes, the previous one. This one. So from here we can go here, right? If I take modulo 15. So let me write on the opposite way. So 15 minus 2 times 7 is 1. So if I take modulo 15, so then I have this equation, right?
Right. Yes, that makes. But
Yes.
when you apply module on the left, I
Yes.
mean, I see that you apply 15 module 15 is 0.
Yes. Yes.
But 2 multiply 7 module 15.
Yes, that remains unchanged, right? Because that is not a divisible by 15, so it will remain unchanged.
Okay.
Right?
And 1 module 15 is still 1, right?
Yes, it is still 1.
Okay, yeah.
Right. So now, so here what I can see is if I multiply 7 with minus 2, then it becomes 1, right? In modulo 15, right? So
Okay.
now from the your starting equation, so if I multiply both sides by minus 2, so this I can do, right?
Mm. So the solution will be 3?
No, not yet. The thing is, this part is fine, right? We can multiply by minus 2, right, on both sides.
Right.
So now combining minus 2 and 7 is 1. So this is x. So x is congruent to minus 6 modulo 15, right?
Okay.
And minus 6 is nothing but 9 modulo 15, because answers we give in positive thing, means non-negative answer we give. So x is congruent to 9 mod 15. So this is the solution.
Mm-hmm.
Right?
So you just apply module 15 there.
Yes.
Yeah.
Fine.
Mm-hmm.
Okay. So next one is part B. So part B is 6x is congruent to 5 modulo 15. So first of all, does it have a solution?
GCD of A and M. That's to be 1.
Yes,
So the
in
GCD,
general, yes, but it will have no solution, right?
it is not 1.
Yes. So it is not 1. So directly by equivalent algorithm, it does not have solution, but you can verify. So modulo 15, right? So we can verify 0, 1, 2 up to 14. So individually we can verify with all the elements whether any of them is working or not, right?
Mm-hmm.
So I think that will not work. So you can verify that.
Sorry?
Yes, you can verify that. So each of the term you can verify. X equals to 0 will not work. X equals to 1 will not work. Like that you can verify these 15 things, and no solutions to this equation, right?
Because the GCD is not a divisor of C.
Right.
So the GCD of
Yes, the simple idea is, so what is happening? So 15 must divide 6x minus 5, right? So this implies 6x minus 5 equals to some 15y, right?
right.
Right. So from here I have 6x minus 15y, that is 5, right?
Mm-hmm.
So here I can take 3 common. So 2x minus 5y equals to 5. But 3 does not divide 5, right? So there is no solution.
Yeah. So 3 does not divide, but also 2x minus 5.
Yes. So their product is divisible by 5 and all are integers, right? So this is an integer, this is also an integer. So it should happen that 3 must divide 5, right? Because 3 is prime. So this equation
No
has no
solution.
solution, right?
Right.
So part C is x square is congruent to 1 modulo 8. So to find solutions to that.
The GCD. Let's start with the GCD.
Yes, but GCD, that one will not work here because it is not a linear equation. It is a quadratic, right? Right. So here actually you can verify. So if x is a solution, x belongs to 0, 1, 2 up to 7, right? So you can verify for which things x square is actually 1 mod 8. So individually,
Okay.
yes. So 0 will not work. What about 1?
1, yes, 1 works.
So 1 is fine. 2?
No.
2 will not work, right? So let me write down all of them. So 3, 4, 5, 6, 7, right. So 2 square is 4. That will not work. 3 square?
3. Yeah, 3 also works.
Yes, 3 square is 9. So 9 is 1 mod 8. So that will work. What about 4?
0.
Right. This will be 0. 5.
25. 1 also.
Yes. 6.
0.
4,
6,
right?
6.
36. So 32 is the nearest one, right? 4, right?
Yeah, 4.
7.
1.
Right. So the solutions are x is congruent to 1, 3, 5, or 7 modulo 8. Right?
You don't count 4 because it doesn't work.
Yes, that will not work. Other things are not working, right?
Okay.
Right. So next part D is so x square is 2 modulo 7. So same idea. So x you have to choose from 0, 1, 2, 3, up to 6, and you have to check which one is working. So this will be 0 then.
1, 1.
Yes. So next 2 will be
1.
no 2 will be 4, right?
Oh, from 2, yeah.
Okay, then
2.
yes, 3 square is 9, that is 2, and then 4.
1.
No, right? 4 square is 16. It is also 2, right?
2, 2, 2.
5.
4.
6, 1, right?
Yeah.
Okay, so solutions are, so x is congruent to either 3 or 4 modulo 7.
Only 2, 3, and 4.
Yes. Right?
Mm-hmm.
So the last one is x square congruent to 3 modulo 7. But this one we already checked here, right? So here 3 does not come, right? So it does not have, it has no solution. Right?
Mm-hmm.
Fine?
Yeah.
Okay. So the next problem it says, problem 4. Part A. So it says that prove that the following divisibility test work. Okay. So the thing that the number A is divisible by 4. Divisible by 4 if and only if the last 2 digits are divisible by 4. Yes. How to do it?
Let's see. Hmm. The last 2 digits. I don't know. How did you
Yes.
establish this?
Yes, so there is an if and only condition, so you have to do both of them, both direction you have to do. So suppose let us assume that A is divisible by 4, right? Then you have to show that the last 2 digits is divisible by 4. So last 2 digits means how should I write? Okay, so let us see through an example. Okay, give me a 4-digit number. Can you tell me which is divisible by 4? Maybe I can just write. So 2316. So this is a 4-digit number, right?
Mm-hmm.
So okay, that you can check that it is divisible by 4. But I can write this as 2300 plus 16, right?
Mm-hmm.
Right. So any number which is more than 2 digits, because it is saying that the last 2 digits are divisible by 4. So A is such a number. I can always write it as some 100 times. So this is nothing but 23 times 100 plus 16, right?
Mm-hmm.
So I can write it as 100 times B plus C, right?
Okay.
So where C is the last 2 digits of it.
Right.
So always I can write like this. So now no. So now since 4 divides A, so we are assuming that A is divisible by 4. So this implies that 100 times B plus C. So this is congruent to 0 mod 4, right?
4 divides A means. Right.
Right.
Mm-hmm.
Yes, but the thing is 100 is also divisible by 4, right?
Right. So it will be 0.
Right. So first part will be 0. So C is 0 mod 4.
Okay,
So
so
what does it say? So it says that 4 must divide C, right?
right.
So that is what they're asking, right? So A is divisible by 4. I showed that the last two digits is divisible by 4. So C was the last two digits, and 4 divides the last two digits.
So the last two digits means there is 100.
Number.
I mean, there is like a 100 factor there.
No, I didn't get you. Tell again.
So if a number has two digits,
Yes.
let's say 216,
Okay.
that means that you can build that number
Yes.
having a 100 as a factor, like
Yes.
100.
100 plus something. 100 times. So this you can write it as
Exactly.
right.
And then when you apply module 4 to that 100 multiply
Yes.
something, I mean, it doesn't matter which number it is, because that 100, when you apply module 4, you will eliminate that.
Yes. Yes. So it is divisible by 4. So that will not matter. So only that part will matter. Only the last two digits will matter.
Right.
So similarly, on the opposite direction also you have to prove. So you have to prove that if the last two digits are divisible by 4, I have to prove that A is divisible by 4. But that is also similar, right? So I can always express like this. If C is divisible by 4, this part is also divisible by 4, right? So, so other direction. So that is, we are proving this side. So here A is 100 times B plus C. And I know that 4 divides C. Right? The last two digits is divisible by C. So then I can always have, so C equals to some 4K. So it's 100 plus B plus some 4K. So I can take out factor of 4. So from here I can conclude that 4 divides it. Okay.
Right.
So I think this is fine, right?
Mhm.
Okay. I think part B, I think now you can do. It is more or less similar idea. So it says that A is divisible by 8. If and only if the last three digits are divisible by 8.
I mean, we can think of like a 3-digit number.
Okay.
Which is, I mean, we will have like 1,000 that multiply, let's say, A.
Yes, A we already have. We have to use something different.
Okay, let's say 1,000
B,
multiply
right?
B plus,
Some C.
let's say, and C is the 3-digit. Sorry,
Yes.
C would
So
be like the 3-digit, right?
right. So last three digits. So C is the last three digits. Yes. Yes. So now.
And then you can apply to that module 8.
Right. Right. So if I'm applying, so first suppose we are doing this direction that A divides A. So this we are assuming. So assume that A divides A. So then
All right.
what we have is so 1000 B plus C. So this is not going to 0 modulo 8.
0 module 8, right.
Is then
Then 1000 B gets eliminated because 1000 is
Right. So this
divisible
is
by
0
8.
mod. Right. So this implies that 8 must divide C. Right.
Mhm.
Right. So now similarly other direction. So we assume that 8 divides C. Then you have to prove that 8 divides 8. How to do that?
So it's going to be 1000B plus 8K.
Right. So suppose C equals to 8K. So then A
Then
is
you factor 8.
right. What is the factor? 1000 divided by 8. What is that?
125.
125. Right. Okay. So yes. So this implies the 8 must divide A. Right.
Right. Yeah.
So let us see the part C. So what C is that a number is divisible by 3 if and only if the sum of the digits is divisible by 3. So what is the meaning by sum of the digits? So let me show you an example. Suppose our number is 123, right?
Mhm.
So then sum of the digits implies so 1 plus 2 plus 3, right? So this is 6. So since 6 is divisible by 3, so 123 is also divisible by 3. So this is the
Right.
yes. So how to do that?
I mean, can you say like a number, let's say 1, 2, 3 is equal to 3 multiply 1, 2 multiply 10, and 1 multiply 100, right?
Yes, yes, that we can write down. So 123. So this you can write it as right. But how does it help?
So you can just say ABC.
Okay. No,
Oh,
ABC.
this is any number, right?
Yes, yes, A is any number. Yes. We don't know that how many digits it have. It can have more than 3 digits also, right?
Mm-hmm.
Yes. Yes. But anyway, tell me, how does this help? Means if I write like this expression. So for this number, let us see how to get from here. Then we can do for the general one.
So I was thinking we can maybe just generalize instead of 1, 2, 3, we would use ABC, and maybe
Yes, yes, that we'll
somehow.
see the generalization. But just tell me for 1 to 3. So if I write this expression from here, how can I conclude that if I check only the sum of digits, then it is sufficient that it is divisible by 3.
Let me see. No, I have no idea.
Yes. So one observation is that so any number that is a multiple of 10. So here, so suppose 10. If I write, so 10 is 1 modulo 3, right?
Right.
So similarly, 10 square, it is also 1 modulo 3.
Mm-hmm.
Right. So you can check that any power of 10. So 10 power n, it is 1 modulo 3.
Mm-hmm.
So let us take suppose a is a n digit number. So we can n can be anything. So a equals to suppose a1, a2. So suppose these are the digits. So this I can write it as a1 10 power n minus 1 plus a2 10 power n minus 2, like that. A n minus 1 times 10 plus a n, right?
Right.
Okay.
Oh,
So now,
see.
okay,
Then you will apply module 3 to everything.
yes. So if I apply modulo 3 to the whole thing, so then what will happen?
Then you will only have like a1 plus a2.
Right.
Plus
So we'll have only a n minus 1 plus a n modulo 3.
module 3.
Right. Modulo 3.
Right.
So now what we can say is, yes. Now how to conclude after this one? So this part what we got is so what we were saying. So this part is nothing but the sum of the digits, right?
Right.
Right. So from here, how to conclude?
Small digits.
So here actually, so what I have shown till now is, so I have shown that A is congruent to A1 plus A2 up to AN modulo 3, right? So suppose we assume the first side that A is divisible by 3, right? So if A is
Right.
divisible by 3, then what happens? Then the left hand side becomes 0, right?
0.
So
You
suppose
will have
3 divides A, so this implies, so 0 is congruent to, so I'll write in summation notation. This you know, right?
right. Yep.
So this will be easier to write. So modulo 3. So I can just move the sides. So 1, 2, and AI 0 mod. So this will imply that the sum of the digits is also 0, right? It means it's congruent to 0 mod 3, so it implies it is divisible by 3, right?
Sorry, say that again.
No, so I started with this assumption, right? The 3 divides A, that the left hand side, that A is
Yeah, the
divisible by 3.
left side becomes 0. Yeah.
Right. So now just we can interchange, right? Because it is an equation, right? I can send this one to this side and 0 to the other side. So
But if negative,
no, this is equation, right? So for example, what I'm showing is, uh, so x equals to 3y. I can write it 3y equals to x, right? I'm just switching the sides of the equation.
okay.
Yes, that we can do, right? Yes. So that is what.
Okay.
So that's why this part is 0 modulo 3. So this is divisible by 3, right? So that is what we wanted to show, that the sum of the digits is
Okay.
divisible by 3. So same idea. The
I
other
see.
side is also same idea. So if we assume that the sum is divisible by 3, so then from this thing, this part will become 0, and here 3 will be there. Sorry, A will be there. So then A is congruent to 0 mod 3, and that A is divisible by 3.
Yeah.
Right?
Same. Yeah.
So I think these problems are clear, right, till now?
Yeah, it's clear. Yeah.
So maybe today we'll stop here then.
Okay.